Welcome, everyone, to this explainer. Okay, let's just dive right into this incredible journey, moving from the physical devices you hold every single day all the way down to the invisible digital data that actually makes them tech. Today, we're zooming from the macro level of how our gadgets interact with the real world, way down into the micro level of bits and bytes, and then finally pulling back up to see how we can actually use this knowledge to fix things when they inevitably break. So, here's our roadmap for today. We are going to look at the four basic functions of every computer, compare analog and digital data, figure out how we measure storage and speed, completely demystify the hexadecimal system, and then finish up with some practical IT troubleshooting. All right, section 1, the four basic functions: input, processing, storage, and output. Let's just strip away all the complex jargon for a second. I want you to ask yourself a seemingly bizarre question. What could a basic, ordinary wall thermostat possibly share with a complex, high-powered laptop? I mean, one is built to run massive, visually stunning video games, and the other literally just sits on your hallway wall. Well, it turns out both devices operate using the exact same four basic functions. No matter if it's a smart fridge, a smartwatch, or a ridiculously high-end gaming rig, it has to do four things. It has to accept input from a user or a sensor, process that data through logical calculations, store that data either temporarily or permanently, and finally provide an output to report the results back to us or maybe to another device. That's the whole shebang. Let's break down the thermostat's decision-making process as our perfect little micro-example. So for input, it gets data from its built-in thermometer. Let's say it reads 77 degrees, and it compares that against your input of, say, 74 degrees. Next, it processes that data. It essentially asks a logical question. Is the current temperature higher or lower than the desired setting? It might temporarily store this historical data in its memory, right? And finally, it outputs an instruction, sending an electrical signal to your AC unit to kick on and cool the house down. Boom. That is a complete computing system right there on your wall. Moving on to section 2, analog versus digital, the language of machines. Now that we know what computers fundamentally do, what language are they actually speaking to pull this off? You know, we hear the word digital thrown around all the time, right? But the crucial point here is that a digital system works by encoding real-world information into a specific sequence of symbols. And it's strictly limited to just ones and zeros. We call these bits. And honestly, this strict limitation is kind of its superpower. Expanding the symbols would just make things unnecessarily complicated. Instead, everything, your family pictures, your favorite songs, text documents, is all stored magnetically or electrically as massive combinations of just these two simple states, on or off. Now compare this to an analog system, like a classic vinyl record. The physical grooves cut into the vinyl are a literal physical analogy of the sound waves. But over time, as the needle drags across it with physical wear and tear, that data physically degrades. Digital data, though, it maintains absolute perfect precision generation after generation. Because at the end of the day, ones and zeros leave absolutely no room for physical wear. Okay, section 3, measuring data and speed. How big and how fast? So we've mastered the basic building blocks. Let's see how they scale up into the massive sizes and speeds we see advertised at the electronics store. When 8 bits group together, they form a byte. And a single byte has enough unique combinations to represent one single character, like the capital letter A, which happens to be encoded as 01000001. From there, we scale up incredibly fast. We go from kilobytes in the thousands to megabytes in the millions, gigabytes in the billions, terabytes in the trillions, all the way up to petabytes, which is a quadrillion bytes. To put that into a somewhat tangible perspective, a totally standard 500 gigabyte hard drive is holding approximately 500 billion individual bytes of data. Think about that for a second. If every single byte was a grain of sand, you would literally have enough to fill up an entire dump truck. And it's all neatly organized so your computer can just instantly fetch your photos. And hey, it's not just about storage capacity either. It's about staggering, mind-blowing speed. When you see a CPU advertised as 3.5 gigahertz, remember that giga means billion. So that tiny little chip is executing 3.5 billion clock cycles every single second, just crunching your inputs to generate an output. 3.5 billion. Looking at these processor speed tiers makes it pretty clear how different devices need totally different levels of power. A 1 to 2 gigahertz chip, that's perfectly fine for a basic smart appliance or a low-powered connected device. But if you're multitasking on a work laptop, you're going to want something in the 2 to 3 gigahertz range. And if you're diving into intense 3D rendering or high-end gaming, you absolutely want that 3 to 5 gigahertz high-performance tier.
But keep in mind, overall system performance isn't just about how fast the CPU clock ticks. It relies incredibly heavily on data throughput. You can think of throughput as the pipeline moving all that data around, and it's calculated pretty simply. It's just the total amount of data transferred divided by the time it took. So if you transferred 10 gigabytes of data in 500 seconds, your throughput is 20 megabytes per second. Things like network congestion, latency, and your overall bandwidth completely dictate this crucial metric.
All right, Section 4, hexadecimal demystified. Base 16 computing. As digital data gets absolutely massive, dealing with endless strings of binary ones and zeros gets super tedious. We really need a shorthand. And that brings us to the sometimes intimidating world of hexadecimal. See, our everyday decimal system uses 10 symbols, right? 0 through 9. But hexadecimal uses base 16. So it takes the familiar 0 through 9, and then it literally just adds the letters A through F to represent the values 10 through 15. Why on earth do we do this? Simple. It makes reading massive values way easier. A huge 48-bit MAC address for a network card can be easily translated into a very short, readable hex string instead of an impossible block of binary. You can really just think of it as a neat mathematical trick. If you want to turn any decimal number into hex, you just divide your number by 16 and record the remainder. Then take your new quotient, divide it by 16 again, and record that remainder. You just keep doing that until you hit 0, and then read your remainders from the bottom to the top. It's just a brilliant way to visually compress massive amounts of data. And finally, Section 5, the troubleshooting methodology, fixing broken systems. So, we've built this incredibly complex digital architecture from the ground up, right? But let's get practical for a minute. What happens when this complex system actually breaks down? Imagine this real-world puzzle. A manager is trying to print an important report, but the printer keeps jamming. Because, well, of course it does. If we map this back to our 4 basic functions, where exactly is the failure happening? Well, the PDF is saved just fine, so storage isn't the problem. No new data is being entered, so input is good. The computer did the processing. The issue is purely the physical paper record. It's a classic textbook output device failure. Really professional troubleshooting requires you to take a highly systematic approach. Honestly, a lot like the computer's own processing logic. Consider another quick scenario. You walk up to a hotel check-in kiosk. The screen displays everything perfectly, but absolutely nothing happens when you tap it. Well, because the display works, output is fine, but because it completely ignores your taps, you have an input failure. You essentially just follow a logical flowchart path, test these diagnostic theories, and then, and this is absolutely crucial, you meticulously document your findings in a journal so the rest of your IT team can learn from the fix. So from the humble little thermostat on your wall to a blazing fast multi-core gaming rig, the underlying architecture remains just beautifully consistent. Knowing how your devices encode analog realities into digital bits, how they process inputs at literally billions of cycles per second, and how they output actionable data, well, I challenge you to step back and apply this system-level thinking the very next time your technology acts up. Thank you so much for joining me for this explainer, and keep exploring the incredible systems all around you.